The transportation industry is the largest industry, one of the largest industries in the world, $10 trillion large. And we believe that someday everything that moves will be autonomous or have autonomous capabilities. As you guys know, there are several very important dynamics that are happening to the transportation industry. One, first of all, the cities are getting too crowded and people are having to move further and further away. The online purchasing phenomenon, the Amazon phenomenon, is causing more and more people to not go to the store, but to wait for the store to come to us. Somebody has to drive those items to us. And as a result of so much increase in population, another billion people are going to come into society in the next 12 years. We already have over 1 billion parking spaces. We have 2 or 3 billion parking spaces waiting for us right now as we speak in anticipation of us needing it. And it's being built in the most precious places in the world, city centers. Autonomous vehicles has the opportunity to reduce the cost of transportation, make it easier for people to get around, live further away from the cities and work, and of course, revolutionize the way we design cities. However, it's hard. Safety is the single most important thing. It is really, really hard technology. It's probably the hardest computing problem that the world has ever encountered. Safety is the most important thing. And as we're reminded just last week, with the fatal accident that happened, we're reminded that this work is ultimately vitally important, that we have to dedicate ourselves, commit ourselves to solving this problem. But we have to solve it step by step by step with just incredible amounts of capability because we know so much is at stake and we have the opportunity to save so many lives in the future if we do it right. And so we at NVIDIA, we're dedicating ourselves to this problem. The grandest of computer problems. Just imagine this. You've got these cars with all these different sensors. Some have a radar that could sense motion, LiDAR that can measure depth but don't see very well in light and snow and fog, cameras with super high resolution but can't see in the dark, infrared that can see in the dark but doesn't have very high resolution. We take all of these sensors and we fuse them together into a super sensor. This sensor, this super sensor, we call them sensor fusion, this super sensor could measure depth, it could recognize motion, it could detect things, it can understand the scene, it could see in the dark. But in order to do this and to compute it in such a high rate of speed as the car is moving and to take action so quickly is incredibly hard. The algorithms, this entire system has never been created in totality, not even once. This system has not even been once created in totality. We're dedicating ourselves to solving this problem. This is the ultimate high-performance computing problem. This is the ultimate deep learning problem. This is the ultimate AI problem, and we think we can solve this. We think we can make just an enormous contribution to this. And so it's a hard problem. The software is hard. The algorithms are hard. But it's also a safety problem, meaning these computers have to continue to operate well even when faults are detected. We have to be able to detect the faults when it happens, and we have to manage the faults, meaning continue to manage the car properly and safely even after we've detected the fault. The level of functional safety required to make this thing happen is just really, really high. A level that the computer industry has really not dedicated itself to understand, because this is something in the transportation industry, is something that is obviously very well understood in the airplane industry. We've dedicated our last 5 to 7 years to understand this entire system. And what NVIDIA is dedicating ourselves to do is to solve the problem from end to end. There are 4 basic pillars to what we do. There's collecting of data. These cars are collecting petabytes and petabytes of data. We take these data and we have, well, collecting of data. I'm going to come back to that. Training models. These models, of course, cars, road signs, people, bikes, trains, motorcycles, trees, hydrants, you name it. Roads, potholes, lanes, curbs. Things are all over the world. The world's very diverse. We have to train our neural network with extreme precision to do this. And then we have to simulate it. Simulation is going to be the foundation of success. And I'm going to talk about that in a second. And then lastly, drive it. Creating the driving computer that's the computer that has the horsepower to compute everything in real time, energy efficient, like all of the energy efficiency comments and examples that I've shown you. Because ultimately, energy efficiency translates to battery life, and battery life translates to mileage, miles of operation, which for many car companies translates directly to their earnings. And so battery life matters. Battery life also allows us to put multiple redundant computers inside the system. The more energy efficient we are, the more computing systems we can put inside the car so that it could be redundant, diverse, and provide functional safety. We have to drive the car, the computer, the system software, and all the algorithms on top. We're building the end-to-end systems. First, let me talk to you about perception. In fact, you can almost piece together all of the work that I've talked about so far into this system. It's called the NVIDIA Perception Infrastructure. We are building a supercomputing infrastructure in our company. There's 660 petaflops of supercomputing horsepower already in our company. This is a giant data problem. I've already just said, each one of these cars are collecting petabytes and petabytes of data every single week. And from that data, we label it in our data factory. We use all kinds of tools and AI tools and trained professionals to label each and every one of these images so carefully. And the reason for that is this. We label it once, and cars in the millions get to benefit it forever. And so we take labeling incredibly seriously. This is not a crowdsourcing problem. This is a professional labeling problem. We have 1,500 people. We're labeling about 1 million images per month. And we're just going to keep on labeling. And from these labels, we're able to create the perception networks that you'll see of incredible levels. We train them on our DGXs that I just mentioned. It's not just a supercomputing problem, it's a software infrastructure problem. In the future, in the past, your source code is your code. In the future, your source code is your data and all the code and all the training methodologies and recipes that you applied in order to create that model, because you want to be able to trace it, you want to be able to repeat it. This infrastructure inside NVIDIA is called the perception infrastructure. It's a massive investment, and it's just something that I'm so proud of. At the end of it, it produces networks. We already have 10 networks inside our car. The self-driving car is not one network. It's a whole bunch of networks, and there'll be a whole bunch more. We already have 10. By the time that we ship in a couple of years, call it 20 or 30. Each one of the 10 networks, there are 10 DGXs assigned to one network, and they could produce experiments every single day. And then we have to validate it and verify it. Many of those DGXs will then have to be used for testing and verification against the entire body of work and the test data that we've stored up over time. Let me show you some of the results. And so, guys, let's go ahead and play it. And so here's a whole bunch of different networks that we've created. This is perception network. You're seeing car detectors and the bounding boxes. You're going to see lanes. Not only do we detect things that we shouldn't collide with, we also have to detect spaces so that that is safe to drive to. Meaning, on the one hand, we detect obstacles. On the other hand, we detect free space. So between those two algorithms, we have redundancy and diversity. We have so much redundancy and diversity all through our system. We do everything 2 or 3 different ways and 2 or 3 different times so that we can make sure that what we ultimately do is right. Distance perception. Here's using an artificial intelligent network that was trained with LiDAR labeling so that it could predict the distance of objects. Weather. We've trained it with so much data that is now robust across all kinds of poor weather conditions. We use cameras for object detection. We use radars for object detection. We also use LiDARs for object detection. Not just how far away they are, but based on the pattern of dots that are coming back our way. The resolution of LiDAR is not as high as camera, but the depth information is really good. Based on the point cloud that comes back, we do point cloud processing on CUDA, which is incredibly good. We do ICP processing, iterative closest point processing, for registration, and then we use deep learning to detect what those objects are. And so LiDAR perception. We do scene perception. One of the hardest things isn't just to detect a light. Intersections where you're supposed to stop or be cautious aren't always properly labeled. And so we have the ability to detect scenes of all kinds of intersections so that we could be much, much more alert. Our path perception is not just about calculating the path, but calculating to perceiving the trajectory of the path that is most comfortable and safe. LiDAR localization. You got to figure out exactly where you are in space compared to an HD map. You want to figure out where you are relatively in space using your camera as well. Camera localization, even to HD maps. So if you had an HD map, we could figure out where we are. It's an additional sensor, in fact. And then, lastly, every single car is also a mapping car. If you have all of this technology inside your car that I just mentioned, your car becomes a mapping car. Which means that when you drive it in the beginning, every time you drive it, you're mapping your space. And so as you know, 99% of the time, we're driving the same route. And most of those routes won't have an HD map in the beginning. And so we'll use our own cars, your car, to map and create a really high-fidelity, three-dimensional map. And then after that, you could use it as an extra sensor to give you additional information to localize within it for safety. Okay? So camera-based mapping. Why don't we show them? What we've done is, every time we're together, I show you a homemade video. And this homemade video are some of the latest clips, if you will, the latest clips of some of our recent achievements. We're making progress all the time. We are far from finished. There are several thousand engineers right now working on autonomous vehicles. We're going to work on this for another 2 or 3 years before we ship in volume cars. In the meantime, of course, we're going to develop and offer development systems and training systems, simulation systems of all kinds. But this is going to be a long journey that is step by step by step. As I mentioned, this is really one of the most complex computing problems we've ever encountered because of the diversity of the problem, the complexity of problems, all the different types of algorithms involved, and multiplied exponentially as a result of safety concerns. And so let me just show you some of the latest clips. Guys? Wow. God, I love you guys. It's amazing how much, as I'm watching this, it's just, all of the software and all the technology that has been created to make all of this stuff happen, it's just, it's washing over me. And it's truly an amazing thing. And the reason why it's so hard, the question is, why don't we just put up a car, and demo a car? Well, it turns out our challenge is we're trying to create a AV computing system and an AV driving flow and infrastructure so that the entire transportation industry can take advantage of this massive investment that we're making and create the future of autonomous vehicles. And as you know, there are all kinds of different sizes and shapes and price points of cars. But every one of them should have the advantages of autonomous capability to either help you drive or keep you safe while you drive. Notice we showed you earlier, Janine, it was a video of Janine, and she's driving. She's pretending like she's sleepy. She's never sleepy. I've never seen her sleepy once. And so she's pretending like she's sleepy, and our AI inside the car is monitoring her, making sure that she's looking in the right direction, that her gaze is still active, that somehow she doesn't appear sleepy, making sure that everything in the cabin is safe and nobody's doing crazy stuff. And so using driver monitoring and cabin monitoring and AI, we're able to make sure that not only is the car doing the right thing, but the passengers inside are doing the right things. This entire infrastructure, this entire system is just such a great undertaking. And we're doing this in a way that is mindful of the fact that we're not trying to build a chip, we're not trying to build a AV system. That in the end, this is an AV computer. And as you know, computers are software defined. One of the most powerful things about today's cloud computing is that the entire cloud infrastructure is software defined. One of the most amazing things about today's cell phones versus yesterday's feature phone is that today's cell phones are software defined. One of the reasons why the PC has become such a revolution instead of a typewriter is because the PC is software defined. Architecture matters. If you're a software engineer, you care about the hardware architecture. And because NVIDIA is not a chip company, we are a computer architecture company. We're a software company. We care about computer architecture. We care about the fact that the software will run on all of these different computers for as long as we shall live, so that we can make the software better and better and better over time, and the entire installed base of fleets and cars that we deployed gets better and better and better and safer and more comfortable over time. And so we created one architecture roadmap, and it basically starts like this. 2 years ago, we introduced Drive PX Parker, and we created, that's a one-chip solution for a very basic car, and then we created a 4-chip solution for Drive PX2, which is the development system for most of the autonomous vehicles that you see around the world. Drive PX2, at the time, when I brought it out, we were laughed at. People laughed at me for bringing out such a large computer. Well, it turns out I did make a mistake. I didn't make that computer large enough. And the reason for that is because the amount of software that the world needed to develop is far more than what anybody realized. And so our basic methodology is this. Then 2 years later, this year, we created the Drive Xavier. Basically, we took 4 chips, the computational capability of those 4 chips in those 300 watts, and we shrunk it into one miracle chip. Xavier is the most complex SoC the world's ever created. It's great for high-performance computing, it's great for deep learning, it's great for computer vision, sensor fusion. It is the largest single chip we have ever made short of Volta. 9 billion transistors. Unbelievable amount of engineers worked on it. Xavier is now sampling. Then from Xavier, we created a 4-chip system. 2 Xaviers and 2 Voltas together. Another running at a very low temperature and voltage, another 300-watt computer emerged. And that 300-watt computer is being used in robot taxi and self-driving car system development all over the world. We're sampling both of them today. Both of them will be in production by the end of this year. Completely architectural compatible, auto grade to the extreme temperatures and operating conditions of a car. It is super energy efficient because battery life matters, redundancy matters, and it is also ASIL-D. This is the first lineup of computers that NVIDIA has ever made that stands up to the highest standard of functional safety, ISO 26262. ASIL-D is a rigor like you have never seen before. From process, because ASIL-D has only been done on small computers, not computers of this type, and not on a software stack of this complexity. This is just a gigantic investment on our part, but it's so important, and we've got to do this right. All of the engineers that are working on this, I want to thank you so much for doing this. Everything from the architecture to the design, the resilience, the redundancy, the diversity, even the documentation, so that it can ultimately be certified and traced all the way back if anything were to happen. Because 100% of all the IP and all of those chips were created here at NVIDIA. We have the ability to produce traceability for as long as we shall live. This is just a gigantic investment, and we take it so seriously. But we're not stopping here. Drive Pegasus, as powerful as it is, multiple of them are being used in self-driving cars, driverless cars. And the reason for that is because there's so many LiDARs, so many cameras, so many radars that are being deployed. So we're not stopping here. Our next generation is called Orin, and we're going to take basically those 8 chips, two Drive Pegasuses, and we're going to put it into a couple of Orins. Incredible amounts of computation in one little chip. And of course, with Orin, there will be discrete GPUs that we will continue to build. There are some code names I won't share with you today. I'll save some surprises for next time. It will create also an amazing processor for autonomous driving cars. Auto-grade, super energy efficient, fully ASIL-D, huge investment. NVIDIA's Drive Roadmap. Let me tell you why this problem is just so incredibly hard. Well, it turns out the world, civilization drives about 10 trillion miles per year. Okay, 10 trillion miles. Just you got to get that number in your head. It's 10 trillion miles. It's 1,000 billion. Well, it's 10,000 billions. 10 trillion miles. 10 trillion miles. And in the United States, 770 accidents happen from 1 billion miles. 770 accidents happen from 1 billion miles. The safety work that has been done throughout the years in the United States has really reduced the amount of fatalities and accidents. And yet, it would take you driving 1 billion miles, society driving 1 billion miles in the United States to produce 770 accidents. And so the question that you have to ask yourself is, how confident are you when your fleet of test cars of 20 over 1 year has driven about 1 million miles? It takes 20 cars driving test drive all year long to test drive 1 million miles. And yet it takes 1 billion miles to have experienced 770 accidents. And we're trying to build a system that is better than humans at driving. And so clearly the amount of coverage, scenario coverage and miles coverage is just not possible in real life. And this is where NVIDIA's skill can really shine. We know how to build virtual reality worlds. And so we imagine this, that in the future, there'll be thousands of these virtual reality worlds with thousands of different scenarios running at the same time. And our AI car is navigating itself and driving and testing itself in all of these virtual reality worlds. And if any of those tests were to fail, it would send us an email. We would jump into it in virtual reality and figure out what's going on. You guys see that? So we have all these virtual reality worlds. Well, let me show it to you today. Mark? So what we're going to show you is this. This is a virtual reality simulator. And before you start, this is the front view, your side mirrors, and your rear view mirror. Okay? Go ahead, Mark. Hey, Mark, how's it going?
Hey, good, Jensen.
One of NVIDIA's veterans.
Thank you. Well, let's start this thing. We're generating our world. We're running 4 simultaneous cameras, as you mentioned. We've got a pretty aggressive driver here in front of us. We've defined a scenario that's causing all the traffic to jam up. But as you mentioned, we got all the cameras. We're running on multiple GPUs, so it's a scalable system. As cars get more and more sensors, more cameras, more LiDARs, we're going to need the horsepower of multiple GPUs. And we're showing that to you right here.
Okay, so we could do, of course, we could simulate daylight scenario. Let's simulate other scenarios.
Okay, why don't we turn the lights out and go to night. So here's the same setup, only now we're doing all the dynamic lighting. So the headlights of the cars, the light posts that are lighting the road, the lights under the bridge as we drive under here, these are all dynamic real-time lights.
And the key here is that the fidelity of the simulation has to be sufficiently high that the sensor stack, all the software that we create, would just operate as they would in real life.
That's exactly right.
Right? So and every one of the sensors needs to have GPU associated with it to generate its view of the universe, its view of the world that it's in. And so today we're simulating with 4 GPUs, with 4 cameras, but obviously we have the ability to spawn off a whole large number of GPUs. So if you have 8 LiDAR systems around your car, you have 8 cameras around your car, you have 6 radars, we have the ability to generate all of that and feed that information into our sensors. And if we are successful in doing that, our artificial intelligence network, all the software that we ran, that we developed, should just work. So Mark, let's turn that on.
That's right. Okay, so here we go. Now this is what our drive stack is seeing on Drive PX. This is all the detection of the cars in the world, the lane detection you're seeing going on, and we've been self-driving this whole time, by the way. So as we ran into that little traffic jam, the Drive PX detected it and slowed down and kept us safe.
And notice we're detecting all the cars, we're detecting all the lanes. But here's the amazing thing. Earlier, the video that you saw were real cars in the real world. We didn't change one line of code iota. The code is exactly the same code that was developed by the engineers. We, of course, copied it over send it over to this data center, and it's running on exactly the same Drive PX, Drive Xavier, and Drive Pegasus computer that we would drive in the car. And as a result, it's exactly the same sensor response. And the perception, the localization, the planning stack all work exactly the same way. And now you're at the end of your...
So we reached the end of that scenario. Can I show you another one?
Yeah, show me another scenario.
So let's switch to the other system.
And so this is one of the beautiful things in virtual reality. We could create whatever scenario we want. And as you know, in test car driving, you could go days, months, weeks, and never run into a weird scenario.
So
we could create all kinds of strange and corner conditions in virtual reality. Go ahead, Mark.
Sorry. So the same adversarial driver just came through. And now we found one of San Jose's finest is in pursuit of him.
You see the cop coming up on the back, the policeman coming up on the back, and it's coming up on the side. There you go.
So we come in, and of course, all the dynamic lighting. So you're seeing the red and the blue lights light up the world. Some of that strobing effect could affect the sensor, so we need to make sure we're modeling that correctly.
That's really terrific. And so, the first is to recreate virtual reality in all kinds of weather conditions and day and night conditions. It has to have the fidelity and the performance that basically simulates reality. 2, that simulation of reality has to be so high, and the computer itself has to be able to run the original unchanged software so that we could test everything as is inside a virtual reality world. And when it passes that, then we can take it and put it into the car completely unchanged. We just OTA it directly into the car, and it should just work. And then 3rd, we could use it to create extreme, corner, rare scenarios, and it's completely repeatable. Every single time that police car shows up exactly the same way.
That's right.
And so we could have the ability, if with repeatability, engineers could debug systems.
That's right.
These 3 fundamental capabilities are made possible. We call this Drive Sim.
That's right.
Ladies and gentlemen, Mark Daly. And so drive sim, just imagine the amount of capability, technology that has been brought to bear. Drive sim, the simulator, but most importantly, the computer inside it and all the driving stacks. And so you got the image generator. This image generator is generating the world. Now, this image generator, in the context of a video game, this image generator is a gaming PC, and the person that would be driving the car would be a person driving the racing simulator. But no, we replace that person with a artificial intelligence AV computer, a self-driving car computer. Inside the self-driving car computer is the Drive Xavier and the Drive Pegasus. And they're connected. Literally, the output of the image generators go into, and there's a sensor adapter, and it goes directly into the drive computers. The exact same software stack runs, and it performs the right actions, perceives the world, performs the right actions, sends back the driving control to the image generator, which controls this virtual reality world. We will have thousands of, we call this drive constellation. Pegasus in the sky, a constellation of them. Pegasus in the sky, a constellation of them. We're going to have thousands of constellations. These virtual reality worlds will all be running simultaneously, and hopefully we could cover a large coverage of scenarios. With just 10,000 constellations, we can cover 3 billion miles a year. Incredible. So, ladies and gentlemen, this is the NVIDIA Drive Sim and our constellation, and it is how we're going to bridge the gap between actual test driving and the trillions of miles and the billions of miles that we need to experience over time. Well, as I mentioned, NVIDIA has created a platform. It's an open platform, and it takes a community to build the future of autonomous driving. It's about the car companies, it's about the trucking companies, it's about mobility service companies. It's about the tier one suppliers that are expert in building these systems and components for car companies. But it's about mapping companies, it's about sensor companies. We work so closely with all the LiDAR companies and all the camera companies to make sure that these future sensors are as high fidelity, as high performance, and as robust as possible, and that the algorithms they use are as efficient as possible. We work with startups all over the world. NVIDIA's platform is an open platform. Last year, we had 320 partners. The year before that, we had 250 partners, and today we have 370 partners. We're working with people all over the world. This is one of the world's largest industries. We're making the fundamental investment for the future of AV computing. The AV computer, all the software driving stack, and the end-to-end development system that will support this fleet and this industry for as long as we shall live, and continue to make it better over time, taking it step by step as we are so mindful of safety. Well, the self-driving car is the first. In the future, robots will augment and will assist us in all kinds of different places. One of the areas that we already talked about is, of course, the Amazon effect. We used to drive to pick up groceries. In the future, groceries will come to us. And this is going to happen in all kinds of different industries. Artificial intelligence and autonomous machines will help revolutionize just about every single industry, making us more productive, making us more efficient, do things that are otherwise impossible to do or too laborious to do or just simply too hard to do. And so we've created a platform like we've done with Drive. We call this Isaac. Today, we're going to release the first little version of that. This is such a great achievement. And so basically, in the future, you're going to be doing simulation as a development system because these robots have to work in a three-dimensional world. And so we created a three-dimensional world simulator we called the Isaac Lab. In the Isaac Lab, we will develop the perception capability, the localization capability, the mapping capability, and the planning capability that is necessary for robots and autonomous machines to navigate these complex worlds. And so we already have our deep learning systems that I've mentioned. And then we take, because it's hardware in the loop, the hardware is driving the simulator. When you're done with the simulator, that hardware should be able to run the entire software stack, and we call that the Isaac SDK. the Isaac SDK running on top of our little computer we call Jetson, we can deploy that. We made a quick little video for you. All you have to do is come to this website, and we'll take and let us know if you're interested, and we'll get you going on an Isaac SDK. So ladies and gentlemen, this is the Isaac robotics platform ready to come to the world. Ladies and gentlemen, Isaac, our new platform, the future of robotics. This is a development system, lots of software developed for it, and of course a simulator that goes along with it, and this little tiny computer we call Jetson. It's been put together for you to start developing the future of autonomous machines. Look, I have one thing I want to share with you. This is something we've been working on, and it's just so exciting. Now, it's never been seen in the world before, and it's far from finished. It's far from finished, and I thought that as a close, I would invite you into NVIDIA's lab. NVIDIA does a lot of things in the holodeck today. We create the future in virtual reality because that's the only place you could create it, and we created this thing called holodeck, as you guys know. And this project is really about thinking through the entire path of how to deploy these self-driving cars into the world. And as you know, when you have a car that is driving by itself in autopilot mode, the driver is the backup system. The driver is the backup system. If you have a driverless car, who is the backup system? And so the backup system likely will be another person. We would like humans to always be the backup system of AI. And so the question is, how do we solve this problem where an autonomous machine has no operator? It could be a little tiny robot like Carter that you saw earlier. It could be a delivery vehicle. It could be a little agriculture, little farming equipment, a little Caterpillar tractor that's roaming around doing things. And there are no operators. And so the question is, how do we create the backup system if something were to happen that we have to go and, if you will, get it out of harm's way? Okay, and so we imagine this. We know that virtual reality has the ability to teleport us. Virtual reality has the ability to teleport us into a new world, into a different world. And so before I'm going to show you a little something. This is Justin Ebert, please. Justin Ebert. Justin is going to help me with this demo. We are currently in the holodeck. I'm going to explain a little bit more as we go through. Okay, but imagine there's a car in the world somewhere, and we need to help it. And so the question is, how do we do that?
Thanks, Jetson. Let's check it out.
So we're in holodeck. We just created a virtual reality car.
We call this Drive Lab, and this is where we have a virtual car where we can take over. Our operator Tim here is sitting on the side stage, and we can see sensors coming in from the vehicle, the remote vehicle that needs help.
Hey, don't go anywhere. Just, hey.
Oh, we're not going anywhere.
Yeah, okay.
Yeah,
all right.
Yeah, we're not going anywhere. We're going to wait and talk this through. So you can see there's
This is so incredible, you guys. This is just utterly incredible.
Yeah.
First of all, I'm going to hand it back to you in just a second.
Yeah, no problem.
What you're looking at is live.
Yeah.
This is holodeck. There's a virtual reality car. okay? The virtual reality driver is sitting right there. His name is Tim Wong. Tim, if you guys raise your hand, there you go. Tim is the virtual reality driver. He is inside this virtual reality car. He is inside the holodeck. He's not with us. That's just a sack of humanity we call Tim Wong, okay? And so Tim is currently in holodeck. He is looking at this virtual world, and you see the video that's being piped in? That is literally live. That is live right now, okay? All right, Justin, take it away.
Yeah, no problem. So yeah, as Justin said, this is actually out back here and in a private area. And let's bring in Tim, so we can show him taking over inside this vehicle here, and let's show that he has control over the car as well. So there's the real car out there. And so Tim, if you can turn the steering wheel a little bit, we can see that we've got.
Oh, come on, cut it out.
Come on, that's fun. Yeah, so he engaged.
Are you guys putting this in your head right now? There's Tim in reality, but he's inside virtual reality, controlling a car that's in reality, but it's not here. Are you guys following me? Okay.
So,
it's like 3 layers of inception right now. The mind clearly exploded.
we've engaged remote drive, you can see, so he knows he has control.
I still remember when we were talking about this, creating this, the people that were explaining to, we're going to build this thing, it was like, okay, explain it to me one more time.
Yeah. You can't understand until you see it. Then it all makes sense. Okay, so I think we've seen this. Let's take a look from Tim's perspective for a second here, and we can have him take off and actually drive the car. As you can see, he's blocked. There's a vehicle here that's doing some unloading, and Tim looked down just a little bit so we can see your perspective, and he can now operate this vehicle around this obstacle and maybe take it to a safe spot in a parking lot for us. And hopefully all. So we're doing this really slowly and safely in a cordoned off area here, and he's going to try to turn off into the parking lot. Now you can see a little bit on the left here.
There's
view is
Tim is in there, guys. There's Tim right there, the invisible man.
And Tim's view is very broad. He can see all 3 screens and get a full perspective of everything that's going on in the car. In the future, we can represent all kinds of LiDAR systems and everything, slowly. So, yeah, maybe we could take a look there.
Look at him.
Yeah.
There he goes. Go, Tim.
There's the team racing after the car there. And let's see if we
you know, what Tim is experiencing right now, he's sitting inside the car, and he feels like he's inside the car, and he feels the car around him. And that's why he's able to, look at that, he parked in a parking space.
Nice job, Tim.
Hey, guys, thank you. Thank you. You guys are amazing. Thanks, guys. Ladies and gentlemen, what do we call this? I have no idea. Yeah, that's right. We call this amazing. So, guys, I'm so proud of you. This is such incredible work, and this is such important work. And as we know, one of the amazing capabilities of the future of autonomous machines is we can go somewhere that we otherwise can't. We could be fixing something. The robot could be fixing something, rescuing someone, and now we could literally, through VR, teleport ourselves into the mind of the autonomous machine and be there. Does that make sense? Teleportation. And VR is our way of doing that. VR augmented with autonomous machines is our way of doing that. Teleportation. The future has arrived. Pretty exciting. Thanks a lot, guys. I'm so proud of you. Okay, we've covered a lot of stuff today. We talked about a brand new, a revolutionary computer graphics technology we call RTX, our dream come true. After all of these years, from architecture to algorithm to AI to integration into all of the APIs in the world and the tools around the world, we have introduced real-time ray tracing to the world finally. We call it NVIDIA RTX, and it will run on a revolutionary workstation called the Quadro GV100 with 32 gigabytes. We also announced our brand new NVIDIA AI platform, all of the new updates from the largest GPU in the world, $1.5 million of value, all for my friends for $399,000. And NVIDIA's DGX2, 2 petaflops of computing, incredible amounts of memory, 512 gigabytes of HBM2. TensorRT and integration, deep integration into TensorFlow and Caldi has expanded our ability to reach the hyperscale workflows around the world. In aggregate, speeding it up by 100x, which allows us to enable people to buy more GPUs and save more money. And not only that, we made it easy to deploy. Kubernetes is now on NVIDIA GPUs. Kubernetes on NVIDIA GPUs. Just really, really exciting. And don't forget, what makes TensorRT such an incredible achievement and what inference is so hard is because of one word. You guys know that word? Plaster, that's right. And so, what a great audience. What a great audience. And then lastly, in our driving stack, we introduced our one architecture. We'll be in production by the end of this year with our first full ASIL-D, full driving computer called Xavier and Pegasus, and the next generation called Orin. But one of the most important things we can imagine doing is to create a simulation environment so that the automotive industry can cover the gap between 1 million cars, 1 million miles, and 1 trillion miles. That level of that many orders of magnitudes of difference in coverage has to be covered in some clever way, and we call that Drive Sim. Running on our server, we call Drive Constellation. And we introduced 2 new platforms, and I'm going to talk about more and more and more every single year so that we can engage these new industries. One of them is Isaac, our robotics platform, and Clara, our medical imaging supercomputing platform. Ladies and gentlemen, it's great having all of you here. Thanks for your support, and have a great GTC.